So today we're gonna finish up chapter 6, section 6.1, and then we will also hopefully get all the way through 6.2 today as well. All right, and so 6.1 and 6.2 will be due Friday at 5. Those two homeworks. Okay. So we saw last time we're doing substitution. And the big thing is, which piece do I make my u? And then how does that affect a du dx exchange? So we've done a lot of these where, for instance, in this one, we made our u the x squared minus 16 underneath, or 1 and 2. When we get to a thing like this, we say, well, this denominator, 4x minus 9, is the inside function. So we'll make that the u as well. So let me go ahead and do this one. All right. We haven't done this one yet. We want to integrate 1 over the quantity 4x minus 9 with respect to x. And so what I do in this case is I set the u to be 4x minus 9. And then I take a derivative of u with respect to x. In this case, that's just 4. So my du is going to be equal to 4 times dx. Now, if you want to make the exchange using this one, you can. I think it's probably going to be easier this time to divide both sides by 4 and say 1/4 du is equal to dx. So my u is going to substitute out for 4x minus 9. 1/4 du will substitute out for the dx. And I'll get the following. 1 over u times 1/4 du. Now that 1/4 is just a constant, so I can pull that in front if I like. I can even pull it in front of here, or I can pull it all the way out because everything's being multiplied. And then when we integrate 1 over u, that's one of our special cases. That's natural log of u. Again, I'm putting parentheses around the u. Other people would put absolute values so that they could make sure you have positive numbers as the inputs. With me, it's fine to just put parentheses around that, make it easier. And then I back substitute. Because I've integrated the du's, there's nothing to substitute with the du. The only thing to back substitute is the u now. And so that is natural log 4x minus 9 instead of natural log of u. Obviously, the final answer therefore is 1/4 natural log of 4x minus 9 plus c. So that was pretty much what we were doing last time, right? Pick the correct u to substitute out. Once you have that, your derivative of u with respect to x gives you your du dx exchange, whatever that happens to be. You just pick the best one, the best version of the du dx exchange. Then do your substitution, integrate with respect to u. And then once you've done that, then you can back substitute to get your final answer with respect to x. So that's what we were doing last time. All of last time. Okay. Let me do one more that's similar to that, just so we kind of refresh on what we were doing last time. This one is secant of 6x times tangent of 6x. Integrated with respect to x. Okay. Again, this one's going to be very, very similar to everything we did last time, So what do I make my u? Well, the thing here is not to get thrown off. The inside function is the 6x. Okay, even though there's two functions here, a secant and a tangent, the thing that's inside both pieces is 6x. So we're going to use that as my u. All right. So we're going to have our u be 6x. Derivative of u with respect to x is just a 6. That makes for a nice du dx exchange of either du is equal to 6dx or 1/6 du is equal to dx. Because I don't have the coefficients out front, I'll probably use this. At this point, we can substitute once again the 6x in both places is going to get replaced by the u, and then the dx is going to get replaced by the 1/6 du. So we end up with secant u tangent of u times 1/6 du. The 1/6 can be pulled out front. And we get secant u times tangent u du. Now, this is one of our trig integrations. Anybody remember what secant tangent gives you when you integrate? What's derivative is secant times tangent?
Tan squared or secant squared.
No, just secant to the first. Close enough. Secant to the first. So when you take the derivative of secant, you get secant times tangent. This was one of the, that was one of those in, back in chapter 5, basically. So that's secant. There. And then you can back substitute. And get 1/6 secant of 6x plus c. So this one was just slightly different in the sense that when we did substitute, our u went in 2 different places. Everything so far had been our u goes into one place. But here our u goes into 2 places. Goes into 2 sections. And then we do a substitution. Now, let me show you one other tricky one. I don't know if this one's I'm gonna make it up on my head because I can't remember if it's in our notes or not. So I'm gonna go one other kind of harder version. This is the one that I wanted to do before we move on. So let's say we have 2x minus 5 in a denominator. And 4x in a numerator. Okay. And I say, let's do this using substitution. This looks like the one we did 2 times ago, right? Kind of. We had a constant over a linear piece. Well, there's actually a couple of different ways to do this one in particular. You can try to divide. But you can do substitution here as well in a manner like we did before. So here's one option of solving this. I'm not saying this is the only option. I'm saying this is one option of solving this. So one option to solve this is to set u equals 2x minus 5. Now I'm going to leave some space because I'm going to come back to this, right? Derivative of u with respect to x is 2. So my du is equal to 2 dx. Now, there's nothing special about what I just did there. That's the exact same thing we've been doing the whole time. And since I have a 4 up here, I may pull that 4 out, factor it into 2 times 2, and then put a piece with the dx. So let's go ahead and do that. So we're gonna do 2x on top, and then I'm gonna factor out a 2 and place it with the dx right there. Now this 2x minus 5, that's gonna get replaced with the u. The 2 dx is gonna get replaced with a du. But notice there's another x hanging around. In this particular example, and in others like it. Because I did a u equals a linear function with respect to x, what I could do is I could say, well, that x can be replaced with a 1/2 u plus 5/2. See that? So if I can solve for x here, I can also replace every x I see with this. Yeah,
So couldn't you just go to the 2x part, because you have 2x on the numerator, and you don't even need to go to the,
exactly. So that's, I was just gonna go backwards one, exactly. And in this case, I could even use the 2x and replace it with a u plus 5, right? So in general, I can solve for x and then plug this thing in. This one I have a 2 up front, so I might as well use this one for my exchange. So what I'm gonna do is I'm going to now substitute in 3 different places. This 2x is gonna get replaced with a u plus 5. The 2x minus 5 gets replaced with a u. And then the 2dx gets replaced with a du. Now I want to rewrite this before I integrate. Because you might say this doesn't look that much better than this. But it turns out it is. It's much easier to divide here than it is to divide here. So if I go u plus 5 over u over u is just 1. And then 5 over u is 5 over u. So I have 2 terms to integrate. I can integrate one with respect to u. That's just 1u, which is u. Integrating 5 over u, that's 5 times the natural log of u. And then I get a plus c. And then I just back substitute for my final answer. So the u gets replaced back with 2x minus 5 for both spots. And that would be your final answer. Now that final answer could be rewritten. Because this minus 5 is a constant, it could be absorbed into the c if you wanted it to. Does that make sense? But the minus 5 in here could not be. This has to be 2x minus 5. So that's one way to use substitution in order to solve that problem. Now, I won't go through all of the steps using the other way, but I will kind of describe using the other way to solve this problem. You'll still have to do substitution. But what you could do alternatively is simplify this rational expression first and break it down. And then integrate. And that's just a division of a linear by a different linear. So you'd want to go 2. You guys know what I'm doing there? Just standard long division. And so if I were to simplify that, this rational expression could also have been written as 2 plus 10 over 2x minus 5 dx. Is that okay? And then what you want to do, since this has 2 terms in it, you want to integrate both of those. However, what I would probably do is I would break this up into 2 separate integration parts. This one you can integrate very, very quickly, 2x. This one would take substitution to integrate, just like what we've been doing. Does that make sense? So I don't know which one's easier, but you would end up with basically the same thing. This, when you substitute, gives you 5 times natural log of 2x minus 5. And so you get that in the end. All right, I'm skipping some substitution steps here, but you get that. And like I said, that is the same thing as what we got here, because this minus 5 is a constant, so it can be absorbed in the plus c. Right? So I don't know which way you like better. I tend to like, if I can do that u substitution from my rational expression like this, I tend to like that better because that's an easier divide. You're eventually gonna have to divide. It's easier to divide by just a u in the denominator than trying to divide by 2x minus 5. Usually. So I like the u substitution first. And it doesn't have to be just a linear piece here. You could have like 4x squared plus 8x minus 7 on the top. And you can do the exact same thing that we did earlier. Or you could do this, where you divide a bunch and then just use substitution on an integral like this. Does that make sense? All right. Now, in this class, I'm not gonna do a lot of substitution with definite integrals. We saw how to use our calculators to deal with definite integrals, and we'll do more of that as we go on. So we're not gonna do a lot of substitution, but I do wanna make note that if you are dealing with definite integrals and substitution, when you do your substitution, let's say we were doing bounds from 3 to 7. And we were going with 2x plus 1 as my u. Okay? When I convert it to integrating with respect to u, it's no longer 3 to 7. Does that make sense? Because the x was from 3 to 7, and that translates to a u of, well, that would be like 9 to 15, because if I'm making my u 2x plus 1, 3 in for the x would be 2 times 3 plus 1. No, that's 7, right? 7. And then 2 times 7 plus 1 would be 15. So my bounds would go from 7 to 15. Does that make sense? So you just have to be wary that if you're integrating with respect to x, your bounds are 3 to 7. But if you're integrating with respect to u, the numbers could change on your bounds. If you convert back to your x's, you don't have to worry about that. You can integrate with respect to u, convert back to your x's, and now you're back from 3 to 7 again. Does that make sense? All right, same thing here, 0 to 9. If you integrate, if you substitute for u, integrate, and then back substitute and come back to your x's, you're back to 0 to 9. But in the middle, with respect to u, you weren't from 0 to 9. Okay. All right. Now that leads us to the next thing. We've done a lot of substitution in the last couple of class periods. However, there are integrals, in fact, like these two, that are not solvable using direct substitution, replacing an expression with u. And that's what most of the rest of chapter 6 is going to be. What if we can't use substitution to solve these? Or at least not just replacing an algebraic expression with an x or a u. So here are two examples where if I just made an algebraic expression equal to u, it wouldn't go so well. So let's take a look at the next section, which is integration by parts. So integration by parts comes from reversing one of our basic rules of derivatives. In particular, it comes from reversing the product rule. You guys remember the product rule? So substitution came from reversing the chain rule. Integration by parts is actually the reverse of the product rule. So the product rule says if we have functions that are multiplied together and I want to take a derivative of the product of those two functions, I take the derivative of the first function times the normal second function. And then plus the normal first function times the derivative of the second function. So for instance, if I have a function that is x to the fourth times sine, I look at the x to the fourth and the sine as a product of two different functions, x to the fourth and then the sine. So I take the derivative of the x to the fourth, which is 4x to the third, times my normal sine. And then I add normal x to the fourth times the derivative of sine, which is cosine. So that's the product rule. So what we're going to do is we're going to take this product rule and we're just going to simply integrate both sides. If I integrate this side, we're going to leave off the plus c's because those will be absorbed. If I integrate this, you integrate the derivative, you get back just f times g, right? If I integrate on this side, since there's two terms, I can integrate each term separately. And then all I have to do to get my integration by parts is move one of these terms over to the left by subtracting it. So if I want to isolate the f prime times g integrated, I just subtract f times g prime integrated from both sides. Okay? And this is my integration by parts rule. So integration by parts says that if you want to integrate some function that can be written as f prime times g, it is f times g minus integrate f times g prime. By the way, these f's and g's all have to be differentiable functions for this to work. In other words, I have to be able to find a derivative. Okay. For this rule to work. At least on the integral, the interval that we're looking at. Now, there are lots of different integration by parts problems, but in this class, we're primarily going to look at three different types. The first type is when I have a polynomial multiplied by a trig function or an exponential function. So polynomial times a trig function, polynomial times exponential function. A second type is when we have a polynomial multiplied times a logarithm. And then the last type is when we have an exponential multiplied by a trig function. When I say exponential, I mean e to the x or e to the 4x or e to the some power of x that's length. Okay. And when we do that, one of these is going to be my f prime, one of these is going to be my g in my integration by parts formula. So I have two parts, an f prime and a g, in this integration by parts formula. And so if I'm integrating the product of two things. One of those things has to be the f prime, the other has to be the g. And that's gonna be the trick, is picking out which function is my f prime and which function is my g. If I have that, then we just apply the formula essentially. Okay? And so that's why I broke it down this way. If it's a polynomial times trig function or a polynomial times exponential, it turns out the polynomial is going to be the g. Don't write that down now, but I'll show you how that works in just a second. Polynomial times a logarithm, it turns out the logarithm needs to be the g. An exponential and trig, you can use either, it doesn't matter. So let's do this example. We want to integrate 4x times e to the 5x with respect to x. Now, you can just take my word, if you try to use substitution, it's not going to make things better. All right? You're still going to have variables in the exponent of e and also in front of e being multiplied. Notice this is polynomial 4x times an exponential function e to the 5x. All right, so this is the type 1 of those problems we mentioned. Now, just as a offhanded comment, integration by parts sometimes takes a lot of room. So when you organize this on your notes, make sure you're organizing it in a nice, clean fashion. Takes a lot of room sometimes. So here's our function that we need to integrate. Because this is polynomial times exponential, what I am going to do is I am going to call the f prime the e to the 5x part. And I'm going to call the polynomial 4x. This is also going to be the case when we have a trig function times a polynomial. Now, we need to get f, g, and g prime. We need to know those things. If I go from f prime to f, I need to integrate going from f prime to f. That's one of the things, e to the 5x, when I find the antiderivative of that, remember that was e to the 5x, and then we divide by 5. You guys remember that from chapter 5? That was one of our things from chapter 5. If you don't remember that, you can, off to the side, just integrate e to the 5x. Now, here's the trick. Going from g to g prime, we have to take a derivative, differentiate. So one of these we have to integrate, going from f prime to f. The other, we have to take a derivative. Now, the reason why we chose the polynomial to be the g is exactly this reason. When you take enough derivatives of a polynomial, they eventually get down to a constant. You see that? And constants are really nice to deal with when a constant is being multiplied times another function. I can just pull the constant out. Does that make sense? So when I want to integrate 4x times e to the 5x, I know that the answer is going to be f times g. Now I know what f is, I know what g is. So f is 1/5 e to the 5x times g, which is 4x, minus integrate f times g prime. My f is 1/5 e to the 5x. And then my g prime is 4. I'm gonna do a little rewrite. Now remember, there's no integration in this part. Just f times g is just f times g. So there's nothing to do here other than maybe rewrite, make it look a little nicer. So there's no integration in this first part. But I do still need to do an integration in this trailing part. The nice thing is this is just a constant times e to the 5x. So that's something that I can integrate fairly efficiently. In particular, this e to the 5x is going to be e to the 5x, and then I would divide by 5. Dividing by 5 gives me a coefficient of 4/25. 5 times 5 is 25. And so that's my answer. And in fact, that's my final answer of what is the antiderivative, what is the indefinite integral of 4x times e to the 5x? Well, it's that. And what's really happening is if you took a derivative of this, if you wanted to check your answer, this first piece, you'd have to apply a product rule on. So you take the derivative, well, actually, let's do this way. The derivative of e to the 5x times normal 4/5 x. That would give you 5 times 4/5. And then you do a derivative of 4/5 x times normal e to the 5x. Derivative of 4/5 x is just 4/5 times normal e to the 5x. And then when you take a derivative here, you get negative derivative of e to the 5x is e to the 5x times 5. If I multiply that by 5, I get 4/5. And then the plus c gives you 0. And so notice what's happening is when you take a derivative, this one splits up into two pieces. One of those pieces is getting canceled out by the derivative of this piece. Does that make sense? So these are the same, these are opposites. Plus 4/5 e to the 5x minus 4/5 e to the 5x. So those are getting canceled out and you're left with this thing, which is what you wanted to get. Right? So if you want the antiderivative of this, you have to include multiple terms so that in this case, start with two terms, derivative becomes three terms, two of which cancel out. That makes sense? So if you're trying to find the antiderivative is this. And it looks messy because you're gonna, when you take a derivative, you're gonna end up with terms that cancel out. Is that okay? All right. Let's do another. I want you to try this one on your own. It's very similar. Use integration by parts to integrate 2x times cosine of 8x. All right, so let me go through this. Biggest thing is, what do you call your f prime? What do you call your g? Once you set that up, everything kind of flows in order. Polynomial times trig function. Polynomial, I set as my g. My f prime gets my trig function. Now the derivative of 2x is just 2. If we want to integrate cosine, that becomes sine, right? Now we have an 8x inside our argument instead of just an x. So it's going to be sine of 8x, But just like when you deal with exponential functions, when you integrate, you divide by that 8 out front. So it's 1/8 sine 8x. By the way, if you didn't know that immediately, that little trick of dividing by 1/8, or dividing by 8, I should say, you could have also, off to the side, did a u substitution with cosine of 8x. And then did that u substitution, and you would have found out that you do in fact get that. Just as a little side note, normally when we integrate, we tack on a plus constant. We don't need to tack on our plus constant over here, because when you throw it into this formula, it'll eventually get canceled out. All right, and the plus constant at the very end will take care of all of our constants. Does that make sense? So if you put on a +5, it wouldn't change the end result. It would just muddy the waters. You can try that if you want, but I won't. Okay, so now that we have our f prime, our g, our f, and our g prime, now I'm going to turn to the formula and say, if I want to integrate f prime times g, that is f multiplied times g minus integrate f multiplied times g prime. Integrated with respect to x, obviously. I'm going to do a little bit of a rewrite just to make things nicer. I'm used to seeing the x in front, and also 2 times 1/8 is 1/4. Be careful in Moodle. Make sure you put that multiplication sign in between the x and the sign if you come across something like that. And this asks me to integrate 1/4 sine of 8x with respect to x. The antiderivative of sine is negative cosine. And because we have an 8x in our argument, we'll divide by 8. So we'll get minus a negative cosine 8x. When I divide by 8, I get 1/32. Then plus c. Everybody okay with that? Minus a negative, I'll put that as a plus just to make it look a little nicer. So my final answer is 1/4 x sine of 8x plus 1/32 cosine of 8x plus constant. That all make sense? Be crazy about it. And again, if you were to track what happens here, this thing, when you take a derivative, splits up into 2 pieces. when you take a derivative of this, it gets one piece, which will cancel out with one of the two pieces over here. And you'll be left with two x cosine 8x in the end. Okay. Now, in both of these examples that I gave, our polynomial was a linear polynomial. And that was nice because when you take a derivative, it goes immediately into a constant. All right? If your polynomial was, for instance, quadratic, like 12x squared, it wouldn't go directly into a constant when we took a derivative. So let's integrate 12x squared times e to the 2x with respect to x. Well, this is still polynomial times exponential. So polynomial times exponential means that the exponential piece is going to be my f prime. And my polynomial piece is going to be my g. So the 12x squared is going to be the g. And the e to the 2x is going to be my f prime. I'm going to integrate to give me the f. That's 1/2 e to the 2x. I'm going to take a derivative to give me the g prime, which is 24 times x to the first. I'll write the first step here. 12x squared e to the 2x with respect to x, therefore, is f times g minus f times g prime. Obviously integrated with respect to x. Now let me clean that up a bit. I'll start writing it here. One half times 12 is 6, so 6x squared e to the 2x minus integrate. That's going to be 12x to the first times e to the 2x with respect to x. Now the question is, how do we integrate this integral here? Well, if you look at this integral here, it's almost identical to that first example we did with just different numbers. So we have to use integration by parts again. For this integral. And oftentimes, because I have to do integration by parts again, and I have a minus out front, I might just stick the minus inside to make my life a little bit easier, so I don't have to distribute the negative sign later. So I either have to distribute the negative sign now or later. Since we have one term right now, we might as well distribute it now. Okay. So I'm going to do an integration by parts for this integral here. And so I'm going to create another system. And in this system, the f prime, since this is still polynomial times exponential, the f prime is my exponential. The g, once again, is my polynomial. That's for this one. Integrate to get f of 1/2 e to the 2x. Take a derivative to get g prime is equal to -12. That's a constant. That's fantastic, right? You want to get constants. Now, be very, very careful. The original one I'm trying to integrate is the 12x squared e to the 2x. So we still are trying to integrate this one. That means I still have this term out in front. And then when I deal with this integral, I'm going to deal with it as f times g. Since I have a plus out there, that makes these things a little bit nicer. F is 1/2 e to the 2x. G is -12x. Minus integrate f times g prime. With respect to x. I'll clean this up before I integrate. (1/2) times -12 is a -6. I have an x times e to the 2x there. I'm gonna do something real quick. This negative and that negative are gonna cancel each other out. So when I integrate this, I'll integrate a plus 1/2 times 12 is 6. E to the 2x. Is that okay what I did there? 12 times 1/2, well, I should say -12 times 1/2 give me -6, and I just negative of negative becomes a positive. Now I integrate and get my final answer. When you integrate this, you get e to the 2x divided by 2. 6 divided by 2 is 3. And then we tack on a plus c at the very end. So that's my final answer on this one. So we started with a polynomial that was quadratic, and we ended up with 3 big pieces, other than my plus c. When I started with linear, I got two big pieces and then a plus c. If you had a cubic, which is third degree polynomial, you're gonna have another extra one and another integration by parts step. If you did a fourth degree polynomial, you're gonna have another term and you're gonna have even another, you'd have to have 1, 2, 3, 4 integration by parts steps. And by that time, hopefully you see a pattern in what's happening. And there are patterns that you can start choosing. Notice that this had an x squared in it, this was an x, now we had, right? So we're taking derivatives of the polynomial as we go to the right, okay? And then we're integrating this, so we're dividing by 2 each time. So the polynomial will get multiplied. When I take a derivative, that gets multiplied by 2, then I divide 2, and I get the 6 back. And then go from positive to negative to positive again. And then if I took a derivative, I would have gotten 6. I integrate and divide by 2, I get the 3. So there's patterns that you could recognize after you've done these things a few times. Okay? And that's what you really do if you get into higher degree polynomials. So if you get into really high degree polynomials, you just start saying, oh, what's the pattern that I'm creating here? And then that pattern just keeps going on and on and on. Does that make sense? So I'm not going to give you anything on a homework or a test that would be integrating a fourth degree polynomial times e to the 2x. Okay. A quadratic would probably be about as big as I'd give you, where you have to do 2 integration by parts. And then beyond that, most people just start picking up on the pattern that's happening. Just so you know, if you did take a derivative of this, what would happen is this first one would split up into a plus b, 2 terms. This second one would be a minus b, would split up into 2 terms, minus b, and let's just say a plus c. So 1 term there would cancel out with 1 term there. And then this last one would be your opposite of the c term. That's probably bad notation, but you guys get the point. You'd have to do a product rule here. You have 2 terms. Product rule here, you have 2 terms. And then that's not a product rule. That's 1 term. So you'd end up with 5 terms, 4 of which cancel each other out. And the last of which is 12x squared times e to the 2x. So there'd be a lot of canceling out in that case, if I took a derivative of that answer. All right, any questions about that? Polynomial times e to a power or polynomial times a trig expression. If the polynomial is quadratic, you're going to have to do 2 integration by parts. 1 first, 1 second. By the way, I skipped this one, but secant squared is a trig function, right? So that's still the same thing. G would be my 10x, f prime would be secant squared, and the antiderivative of secant squared is tangent. This is another quadratic times trig function. This one has multiple terms, but it works in the exact same way. I just let my g be x squared plus 3x plus 1. And that polynomial. And I let my f prime be my sign. And then I'm going to have to do 2 integration by parts with that one. Okay. I'll skip that one. Or at least those two that I just mentioned. So let's move on to the other type of integration by parts. The second type we mentioned, which was polynomial times natural log. Or technically any log would be done this way. But in particular, we have a polynomial x squared plus 3x plus 1 multiplied times natural log of x, all integrated with respect to x. Now, we just dealt with a lot of polynomial times e to a power. And in those cases, we kept our polynomial as the g. However, in these types of integration, we are going to do the opposite. If I tried to let my f prime be natural log of x, that means I have to integrate natural log of x. And most of us probably don't know that offhand. And if you do know that, it's actually more complicated than this. So it doesn't do you any good. We'll talk about what it becomes when you integrate that in a little bit. But so what I have to do, if I have natural log, is I have to make my g the natural log of x. And again, this will work for any log base 6 if you wanted to make, if you had log base 6 instead of natural log. And then my f prime is going to be the polynomial. So I'm going to have to integrate the polynomial this time. In this instance, that gives me 1/3 x to the third plus 3/2 x squared plus 1x. If you wanted to add a plus c, you could, but it's irrelevant at this stage. It'll eventually cancel out. All pan out the same. And then we have to take a derivative of my natural log. Now, here's the nice thing about a derivative of natural log. Derivative of natural log is 1/x. And that's really nice to have to multiply polynomials with. What's going to happen when I multiply x to a power, let's say x to the 9th times 1/x? Well, you're just going to get x to the 8th. Or if I multiplied x to the 5th times 1/x, it's going to get x to the 4th. So 1/x is really nice to have to multiply to polynomials. And that's the whole trick. Okay. So let's remember what our rule said. Our rule said if we're going to integrate f prime times g, natural log of x. So integrate f prime times g. We need to take f times g by the way, I'll go back to that in a second. Minus integrate f times g prime. So f times g minus integrate f times g prime. And when you clean up your f times g prime in that integration, that fact of multiplying through by 1 over x and reducing the exponent by 1 comes in really, really handy. 1 over x times this term is 1/3 x squared. 1 over x times this term is 3/2 x to the first. 1 over x times x is just 1. And we're integrating this, which happens to be a really nice polynomial to deal with respect to x. And so that integration is nice to do. Let me rewrite this. When you integrate that polynomial, you're going to get 1/9 x to the third plus 3/4 x squared plus x to the first. And then we tack on a plus c at the very, very end. Okay. If you want to distribute the minus sign into all three of these terms, go right ahead. Moodle should interpret it as correct, whether we have parentheses in there and the minus sign on the outside, or if you distribute it into all three terms. So Moodle should count it correct either way. Same thing here. If you wanted to multiply natural log times all three of these terms, that's fine. You just want to leave it as this polynomial in parentheses times natural log, that's fine too. However, do not, and I just mentioned this because I've seen it, a lot of people will do the integration on their homework and then forget the parentheses. And, you know, the minus sign goes out in front of this one, and then do a plus sign out in front of this one, and then a plus sign here and a plus C, and they didn't know why they got it wrong. Right? This is different than this. We have to put parentheses around my integration here or distribute the minus sign to every term. And the same thing goes for this component too. If you forget the parentheses, and you just write in plus x times natural log of x, well, the natural log of x is only being multiplied by this one here, not the entire polynomial. So Moodle will count that as wrong, obviously, because of that. So be careful with including the parentheses around your entire polynomial, is what I'm trying to get at. Any questions about this? Notice that in this case, we started with a quadratic, but we only had to do one integration by parts. With the natural log of x, no matter what the polynomial is, it's just one integration by parts to get to your final answer. So that's kind of nice this way. So even if we have something like x to the 17th times natural log of x integrated with respect to x, it's just gonna be one integration by parts. Go ahead and try this one on your own. All right, so in a lot of ways, this one's, just because it has fewer terms, even though it's a higher degree polynomial, it's got fewer terms, so it's kind of easier to deal with than our previous ones. I don't have to worry so much about the parentheses when I only have one term. So f prime is gonna be my polynomial, my g is gonna be my natural log, g prime becomes 1/x. When I integrate x to the 17th, I get 1/18 x to the 18th power. So integration by parts says when you integrate f prime times g, it's f times g, 1/18 x to the 18th times natural log of x, minus integrate f times g prime. That's 1/18 x to the 18th multiplied times 1/x, integrated with respect to x. Again, I don't have to worry so much about the parentheses if it's just a single term. If you do want to add parentheses, to make your life easier, that's fine. Over here, what's going to happen when you simplify is you'll get x to the 17th. More specifically, 1/18 times x to the 17th. That we need to integrate. And so you get this polynomial 1/18 x to the 18th multiplied times natural log of x minus, when I raise the power by 1, I get x to the 18th, dividing by 18, 1/18 divided by another 18 gives you 324 in the denominator, 1/324, and then plus c. Since I have a single term, I don't have to add parentheses, but if you want to add parentheses, you can. And just so you know that on Moodle, when you type in your plus C, type that plus C outside of everything else. Okay, technically you could put the plus C in the parentheses as well, if you really wanted to, but just so everybody's consistent on Moodle and consistent with the answer, we put the plus C on the outside of everything. Okay. On the outside of that parentheses. So that's it. So every time we have to deal with natural log multiplied times a polynomial, this is the way we deal with it. And one of the reasons we wanted to is that because if we try to make f prime be natural log, we have to find the antiderivative of natural log. Turns out it's not simpler than natural log. Anybody know the antiderivative of natural log off the top of their head? Anybody know just the antiderivative? How to integrate natural log of x with respect to x off the top of their head? Other than me, obviously. You know what you could do to find it?
You substitute with x somehow.
You know what you could do to find it? You could do integration by parts. With the polynomial out front just being the number 1. Okay, this is actually how it's done. So let's do that. Let's just go through the motions. Let's use integration by parts. I didn't go back to my notes, but this was the next one of the next ones on the notes. Integration by parts to figure out the antiderivative of natural log of x. So you use the polynomial of 1. When you integrate 1, you get 1x to the first. Obviously, the natural log of x has derivative 1/x. So that tells me that if I want to find the antiderivative of natural log of x, I can take f times g, that's x times natural log of x, minus integrate f times g prime. Now my f times g prime is x times 1/x, which is just 1, as in the number 1. And the antiderivative of the number 1 is x. Plus c, obviously. Tack on a plus c at the end. So if you did try to use natural log, when you do the antiderivative, you get x times natural log of x minus x, which is way messier and still includes natural log. So you didn't make your life easier. Okay. So good. anyways. Now you know the antiderivative. X times natural log of X minus X plus C. So that's how to deal with that second type of integration by parts that we're gonna see. Any polynomial times natural log, even if that polynomial is the number 1. Right? Like we had here. We can still use integration by parts to integrate. Now, the last option is the messiest option. I'm going to show you how to do this once. This is not one that we do a lot of, but we'll do maybe a couple of times. This is when we have a trig function like sine of 4x multiplied times an exponential function, like e to the 2x. So this is our last type, and it is going to be the messiest type. There you go. Trig function times exponential. Now it turns out it doesn't really matter which one I call my f prime and which one I call my g. When I take derivatives of trig functions like sine, it's just going to give me another trig function. And that's going to happen over and over infinitely many times. Derivative of sine is cosine. Derivative of cosine is negative sine. Derivative of negative sine, or sorry, negative cosine is negative sine. Derivative of negative sine, negative cosine, right? I misspoke there somewhere. But we get an infinite loop of derivatives with trig functions. And the same thing, if I just take derivatives of e to a power like 2x, I get 2 times e to the 2x, and then another e to the 2x, right? E to the 2x keeps showing up over and over and over, which is different coefficients. So both of these are not going to go away when I take derivatives over and over. So I just got to pick one. Oops. To be my f prime, and the other to be my g. Derivative of sine is going to be cosine. Since we have 4x on the inside, we're going to multiply by 4 on the outside. Well, this is chain rule. Multiply times derivative of the inside function. Derivative of 4x, just 4. And then when I integrate e to the 2x, I get 1/2 e to the 2x. All right, so this integration is going to be f times g minus integrating f times g prime. Now, hopefully this is not too much. When I do it, my f times g prime, I'm going to automatically multiply the 1/2 times the 4, just so I don't have to rewrite a number of times. So that's 2 e to the 2x cosine 4x dx. Good. We okay with that? Just multiply the 1/2 and the 4 together, so I don't have to write another line. Now you'll see this is still trig function times exponential. Trig function times exponential. So just like we did with the quadratic, we're gonna do another integration by parts. With this integral. And because I'm doing that, I'm going to also kind of distribute that minus sign in here. I'd like to put it with a cosine. Is that too much? If you wanted to put it on the outside, put it on the outside. I'll put it there. Is that okay? So I'm just distributing that minus sign since I'm going to do another integration by parts. And my other integration by parts, since I used f prime as the exponential, I'm going to do that again. F prime is going to be my exponential, and I'm going to call that 2e to the 2x. And my g is going to be my trig function. And I'm going to take the negative sign in there with the cosine. So the negative is going to be attached to the cosine. Everybody know why that is? When you take a derivative, you get negative of a negative sign, which gives you a positive sign. So let's integrate. I get e to the 2x, and I divide by 2, and I get a 1. When I take a derivative, I get negative sine of 4x, and then I'd have to multiply it by 4. Negative 4 sine 4x, negative is a positive 4 sine of 4x. So let me rewrite what we have now. Sine of 4x times e to the 2x dx equals 1/2 e to the 2x sine 4x. That's what I got here. This integration by parts gives me f times g. That's negative e to the 2x times cosine of 4x. In fact, I'm just going to make that a minus. Is that all right? And we'll do plus and negative. It's fine. Okay, that f times g, right, this way, minus integrate f times g prime. Does that make our lives any better? Yeah. Why did that make our lives better?
Because you have the integration of e to the 2x sine 4x on both sides of the equation.
Exactly. I have the same thing on both sides of the equation, e to the 2x sine of 4x under an integration. And so what I can do is I can do this really nifty trick. And I'll do this in multiple steps. I'm just going to rewrite this thing on the end. as I'll pull out the 4 in front. And I get e to the 2x sine of 4x. So I get this same integration that I started with back, but now I have a minus 4 out front. And then, even though this is super messy stuff, from here on out, it's just gonna be basic algebra. Okay? I'm going to add 4 times this integration to both sides. Doesn't matter if the sine of 4x or the e to the 2x comes first or second, right? They're the same thing. By the way, this coefficient is a 1, right? So what I'm doing is I'm adding 1 integration plus 4 of the exact same integration. And I'm getting 5 of that integration is equal to this. Now, there is a caveat. When I move this over, there was gonna be a plus c at the end here, okay? And this antiderivative and this one might be different by a constant. So I do have to just realize at the very end, I'm gonna throw on a plus c, okay? Because I moved that integration over. But other than that, that's what we got. So let me write down what I have. Over here, 5 times that integration is equal to 1/2 e to the 2x times sine of 4x minus e to the 2x times cosine of 4x. Again, I'll leave off the plus c at this stage because I'll tack it on at the very end. In order to get rid of this 5, I'm just simply going to take both sides and multiply by 1/5 or divide by 5, whichever one you prefer. I'll multiply by 1/5. And that tells me that when I do my integration of sine 4x e to the 2x, I'll distribute 1/5 times this term becomes 1/10 e to the 2x sine of 4x. 1/5 times this term is a minus 1/5 e to the 2x cosine of 4x. And then again, I have to tack on that plus c. You could tack it on at that stage, but 1/5 times constant is still a constant. So we just leave it. I tend to leave it till the very end, to tack it on at the very end. But so that's the messiest type of integration by parts that we do. One that involves trig and exponential. And you essentially do 2 integration by parts and you get back to some constant times your original integration. And then you move that over. Now, this came out to a really nice coefficient of 5. They don't always come out to nice coefficients. Sometimes the coefficients are like, 27 over 38. And then you're adding that to 1 and multiplying by the reciprocal on both sides. So sometimes they get some really nasty numbers. But the general concept and the general principle is exactly this. Okay with that? And I hope I didn't make any mistakes on my coefficients there. If I did, I'll apologize, but I try to keep track of it. All right. Well, that is basically it for 6-2. I might do another one of these, just a refresher, starting next class period. But you have all the tools you need to complete 6-2 homework and 6-1 homework by this Friday. So please try both of those, try to complete both of those homeworks by this Friday. If you need an extension on 6-2 because you're not real comfortable with this one yet, then just ask me and I'll give you an extension on that.
6-3 also says it's due tomorrow.
Yeah, I'll postpone 6-3. Yep, so I'll get to that. So I'll postpone 6-3 until next week. Because obviously we had to cancel class on Tuesday, so. All right, I'll see you next week.
Do we have to distribute it in Moodle or can we just leave